All right, so let's talk about non-separable data, how to deal with that when we are working with this fat margin hyperplane. And then when we talk about non-separability, this can be of two types. The first one is shown here. So here there is some non-separability in the sense that we have these points. But what we're doing here is that we are still using this linear separator that tolerates some error, right? And we've done that before, so we're tolerating like some amount of error, but we still are using a linear separator. Now the second example here is the example that we've looked at before. That's the non-linear transform. We can apply the same process as we did with the linear model, that is transform the data to a z-space. The non-linear model use all the machinery of the non-linear feature transform, and then eventually in that z-space you can apply your favorite algorithm. It could be any linear model. In our case, it is the fat hyperplane. All right, so once we've like transformed this to a z-space, what we can do is we will get some form of linear data in that new space. And then eventually I can use the quadratic program that I formulated in the z-space. And then if a new point comes in, I'll take it to the z-space and then based on that decide where it lies essentially. So all the steps of nonlinear transform still hold. But now we are going to do something for this like general case of non-separability and allow some kind of penetration through the hyperplane, and that's known as the soft margin optimal hyperplane. So let's look at what it is. Now we're looking at soft margin optimal hyperplane. All right, so what is that? Let's talk about that. Okay, so until now, what we have discussed, the fat hyperplane with the margins, is the hard margin hyperplane. That's known as the hard margin hyperplane. Now, if we allow some data to penetrate through the margin, let me show you what I mean. Let's say this is my data. Okay, and then these are the, all right, and we know that the margins will lie through, like pass through the support vectors, and this is my hyperplane. All right, so if there was a point here, somewhere here, let's say, that lies this side, then this is like non-separable, right? But what we can do here is that we can allow, if you like think about this, what has happened, like ideally speaking, this should lie somewhere here. But thinking about this, it has like penetrated through this, right? It has penetrated through this hyperplane margins and is lying on the other side of that, right? And what we do in soft margin optimal hyperplane is that we allow some level of penetration through the margin, unlike the hard margin. And we call this soft margin. Why? Because when the data is not non-separable, we are allowing some level of penetration. Now, what does it mean in terms of like solving the actual hard margin problem? Let's look at the original hard margin problem. Well, and this, by the way, was hard margin, this thing here. And now we allow some sort of like movement of points from this margin up there. So then obviously something needs to change in the original optimization problem. So the original one looked something like this. And then the constraint was the separability constraint that kind of enforces separability was something like this, right? So this constraint here, if you remember, this enforced separability. And when we solve this problem with like the current problem, then we get like hard margin, right? But if you remember the original problem, then like we converted some constraint to this inequality constraint. Originally, when the original condition of separability was something like this, right? So let me write it again. Original condition of separability looked something like this, right? Yn W transpose Xn plus P equals 1. Okay, so then we decided that we like loosen this a little bit, and of course, like there are like some data points always accomplish that equality, and those are the support vectors. So essentially, when this equality holds here in this constraint, that's when we get those support vectors that lie on the margin, right? So the support vectors, if you think about them, the support vectors are some points that saturate this condition, right? They are the ones that help us arrive at that equality. Okay, so how can we utilize that idea to allow some kind of penetration through this margin, right? So we can do something to the constraint essentially, because we know that this is like these points are saturating this constraint. These support vectors are the ones that are saturating this constraint, and we can loosen that a little bit, right? And let's look at what we can do essentially, like in terms of the optimization problem itself, what can we do? Again, let me make a picture of what we are trying to do. This is the margins and this is the hyperplane. And let's say I have like these points lying on. These are my support vectors here and here, right? And so I'm like, I'm going to box them. Let's say these are my support vectors, all right? And then there is a point here that moved to the other side, right? So this like penetrated, I would say that penetrated from through this margin to this side of the hyperplane, right? So sometimes that penetration, uh, the like the distance from this hyperplane is denoted by a quantity that that is utilized in my constraint to allow this penetration. What I'm saying is this, like this penetration indicates that this separator is not separating the data. Therefore, for each of these points, like on the wrong side, we can update our constraint in a certain way. Okay, let's say this distance from here to here is some epsilon or z, whatever you like to call it, this kind of a symbol. And I'm just like trying to stay consistent with the textbook. So if we are allowing this, we are allowing the penetration through this cushion, right? And if like we are allowing this to penetrate, what we can do in our constraint is that we are saying my yn w transpose xn plus b is greater than 1 minus this whatever this symbol is, right? Minus this z, and or let me like make it more convenient because I'm not 100% like comfortable with this. Let me call it z, right? Uh, Here, let's call it this z. All right. So each point is allowed to penetrate. We don't know by how much, right? But think about like what is this penetration doing? If this penetration is large, let's say my like the point is like pretty deep inside the other side, and all my, so if I'm thinking through this constraint and all my w's they just like go to 0, then I can have an infinite cushion or an infinite margin, but that is useless, right? So basically we need a way to figure out this penetration, and we need to figure out something about like what values should it take. So of course, because we are allowing penetration, this has to be first of all greater than 0, because this is like some finite penetration, right? So as like going back to how much it should be, well, as I said, if I'm allowing like a very big value, and let me write it here. So if I'm saying this can go to infinity, which is like huge, and my weights are all 0, then there's no meaning to this cushion. There is no meaning to this margin. So because this is the impact on the cushion of this penetration, we have to figure out a way to penalize this penetration, right? Because this is like not good. So maybe we can penalize it. We can add a penalty somewhere. And basically what I'm trying to say is we want this penetration whenever it's necessary, but we don't like a lot of it. So what we'll do is we'll penalize the sum of the penetrations of all the points, right? And also the amount by which we can do that. So what I'm trying to say is that my final optimization problem and my final optimization problem will look something like this. What I'm saying is minimize half u transpose w, right? Plus the sum of these points that are moving on either side of the cushion, the wrong side of the cushion. So sum them up all and also control them by some constant or some value, right? This is like saying that the amount by which we can penalize this, right? So this is the amount by which we can penalize this penetration, right? And then the new constraint that we just came up with, which is like subject to NW transpose XN plus B greater than equal to 1 minus Zn, where Zn is greater than equal to 0. So that's like a positive penetration. Now, if we solve this problem, we are allowing some penetration, but we are also penalizing too much of it. So here you can see we are penalizing too much of it. Now, think of this summation of Zn over all n, of course, as an in-sample error with respect to the thick separator, right? And of course, like we are penalizing based on like how many points are penetrating, right? So this is in some respect an in-sample error or like an representative of in-sample error. Now this problem here is known as the soft margin optimal hyperplane. Okay, let me write it down. Soft margin optimal hyperplane. And what does that signify? So this gets us a fat hyperplane with some margin violations, right? And those margin violations are given by this term here, right? So we are doing some margin violations, we are allowing that, but not too much of that. So that's like a penalty. If you've like taken optimization classes, you know this is like similar to an optimization formulation with some slack variables, right? So the variables that we need to determine are my weights, my bias, and my z's. So that's what we want from the optimization problem. So I'll add that. So we are minimizing over what? The w's, the b's, and the z's, right? So the variables that we need to determine, let me also write it here. Variables that we need to determine are w, b, and z from the optimization problem, where we want a large margin subject to a small in-sample error. We always want the in-sample error to be small, right? So if you look at this like this objective function itself, you're saying we want a large margin subject to a smaller and smaller in-sample error. We don't want this thing to grow. And this reminds us of something that we have looked at before, right? And that something is regularization, with the exception that in regularization we were minimizing my in-sample error with some penalty term, right? So earlier in regularization, maybe we can, if you remember, in regularization, okay, this pen is weird. In regularization, what we were doing was we had the penalty in the form of model complexity. So penalty was complexity of the model itself, right? In this case, we have this term, this penetration itself, right? So it's the size of the margin, essentially. So that means like now in this soft margin, we have the size of the margin, which is like pointing to something that's robustness, right? All right. A little bit about C, the parameter C that we introduced, that's like pointing to the amount by which we can penalize the penetration. So that C acts as a regularization parameter. It's very similar to the regularization parameter that we looked at earlier. I think we called it lambda, not exactly sure. But the only thing in this optimization problem is that we are focusing more on in-sample error. For example, a smaller e, right? If this, sorry, not e, c, smaller c means more robustness, right? So this is like a more robust model, and that means more regularized, right? So more regularized. And then if there is like a large c, larger the value of c, that means less robust, right? So less robust. All right. Another way of thinking about it is like, let's say if c goes to infinity, right? It's huge, it's really big. Then what is happening? Well, we can recover the hard margin when data is separable, of course. So here you are like recovering the hard margin. So that's the extreme. That's where we started from. All right. So now there might be cases when data is separable and you still want to use hard margin, right? And when, like, let's look at an example, right? So where we have like our data is separable, but we don't really want to go and like allow any kind of movement on the other side. And this could be a scenario when we have like, let's say a point lying on the other side, but it's like very close, right? So then we really want to do the hard margin. For example, let's say we had a hard margin here, and well, there was a point that lies somewhere here from this set. We still want to use the hard margin and not allow any kind of movement of the points through, like not, we don't allow penetration, and so we are like tolerating that error in some ways, right? Now what, I mean, it is possible, right? Because we are just thinking that this particular point that moved towards, like penetrated through the uh, cushion could be a one-off case, so I'm allowing that. And if, like, we are using soft margin, what we are doing is we are allowing some in sample error to get a more robust solution, right? So of course it's totally up to us whether we are trying to allow the penetration or not. It depends on the problem as well. Okay, let's look at some examples with the value of C, because like C seems to be an important parameter for this optimization problem. So here, and again, we're looking at non-separable data. That's when mostly we use soft margin. As I said, we can use hard margin in problems in situations like these, in cases like these, when we think that it's just like a one-off case or some measurement error is there or something with the problem. So here is the non-separable data. The first picture is showing us, and this is like the complete formulation of the soft margin here. And this one here is showing us when C is 1. Okay, so C is like really small. We are focusing more on the width because the second term, this one here, doesn't contribute as much, right? So we get a wide, thick separator with lots of penetration, right? It's allowing a lot of penetration. Of course, this has a finite value, but then we are controlling it through C. The second one here, which has like C equals 500, the margin shrinks, and we are obviously allowing less penetration, right? So that's the difference between C equals 500 and C equals 1, which is telling us, right, the choice of C is like a trade-off between the thickness of the hyperplane and the in-sample error, right? So it's like a comparison between robustness, or trade-off, not a comparison, right? Rather, I would say robustness versus in-sample error, right? And also this points us to the fact that the C is specifically important, right? C is playing an essential role when we are talking about soft margins, especially with non-separable data, right? Let's look at another example here. So this is soft margin, and as I said, the choice of C is important. And even with like separable data, we can, I would say, um, still like choose with separable data, we can choose soft margin because we have this choice of C with us, right? So with the choice of like C equals infinity, we can recover the hard margin. So what is this like C essentially doing? It's quantitatively defining the tolerance of in-sample error, right? So let me also write it down, and that's why this is what this is emphasizing, that we are quantitatively defining the tolerance of in-sample error. All right, and so here's a comparison of like a very small c. So the this like thickness is huge, allowing penetration, and then with the increase in the value of c, as you can see, finally with like a huge like c, really big, or not, if not infinity, but like really big, you can recover the hard margin, as I said, right? So what I'm saying is how much to what exactly are we doing? We are basically, with the help of C, deciding how much to penalize margin violations, because these are margin violations, right? That we are allowing these things to go inside the cushion. So then how much to allow that, how much to allow the violations is decided or controlled by C. Okay, and so then finally this thing here, this for the soft margin, again, this is an optimization problem. And another important observation here is that this is also a quadratic program. And this is usually left for the students to again prove, just like we did with the hard margin. So you just like have to figure out the Q, P, A, C variables and just show that this is a quadratic program again. And so we know how to deal with the variables, how to solve this. Okay. Also, a little bit of discussion is required. Let's talk about the non-linear transform and support vector machines. So, or support vectors, or fat margins rather. That's what we've been calling them until now. So what's happening here is that we are using regression for classification, hence the pseudo-inverse algorithm, and this polynomial transform of order 3, right? So as expected, the model, of course, fits the data. In fact, I would say to the extent that it overfits. And we know why, because this is a higher order polynomial. Most likely it gets the perfect separator. Now in this one here, what we are doing is we are using again the third order polynomial. And in the third order feature space, we use the fattest separator instead. So that's the algorithm we are using, not the pseudo inverse, but the fattest separator now. And see what happens, right? It almost like it's excellent, I would say. It almost produces the target function, right? And yeah, like the we have like how many? 1, 2, 3, 4, 5, 6 support vectors, right? And of course, like you can see the fat margin here, right? And if we like keep doing this, right? And so you might be like thinking why the thickness here is not consistent with what we saw. Like it used to be some given constant thickness, and that's because we did the fat hyperplane in the Z space, right? And like if you think about the separations, like we just have 6 support vectors. So we have like very small number of support vectors, although we are in the third order space. And now like we've come back to the X space, of course, and that's why you can, if you're wondering about the varying thickness of the hyperplane, in Z space, it's still the same. Okay, so and then finally we look at this like second order one, right? So what's happening in the second order? Except like we get a very similar sort of separator, the fat hyperplane, except that it's like more, I would say, smoother as compared to this one. And the number of support vectors is 5. All right. Again, this also is a good result, I would say, right? So what's really happening? What is the theory behind these two, like at least that we need to understand? And so we have this flexibility of the third order polynomial, but we also have the constraint of the fattest separator. So effectively, like the number of degrees of freedom are lowered, right? So my error for like the cross validation error, which was related to the number of support vectors, not degrees of freedom, plays a role here. For example, like for the second order polynomial, we have a nice separator as well. And just like going from second to third order, right? I've almost doubled the dimension of the space, but my support vectors went from 5 to 6, which is not double, not even close to double. So this, what is this pointing us to? Well, we have talked about that before. So this means we can go to higher dimension, still get good results because we have the robustness of the fattest separator, right? So that's what we are talking about here. Okay, so that's an excellent result, and that kind of tells us that it kind of gives us an idea of going to higher dimensions is not that difficult with a fat separator. All right, so this, as we said, like going to higher dimensions seems like something doable because we still have the robustness of in the model. So can we go to higher dimensions? Well, right, in higher dimension, we can control overfitting with the number of support vectors. And so, yes, we can go to higher dimensions, but like up to what extent can we keep going to higher dimensions? Like, is it infinite? Can we go to infinite dimensions? Now, if we can control the number of support vectors and like the margins are huge, right? So basically we are trying to keep the bound on my uh, CV, the cross-validation error. So then I know that I can control my E out. I have a way to control my E out in some ways, right? and then also benefit from higher dimensions because my number of support vectors is not going out of control, right? So yes, I can go from like go to really higher dimensions, but what like a lot of things that come into our mind is like how do we go to the like infinitely many higher dimensions? First of all, does that impact my efficiency at all? Because this seems like this is going to be some really complex space, and we would require some kind of feature transform. So what type of feature transforms will we require in that higher dimensional space? So all those questions are important, and although we have some idea of moving towards like working within the higher dimensions, but we have to address these questions. And so what we're going to do is in the next lecture, we are going to see how we can move to infinitely many dimensions if we can. So that's it for this lecture. Thank you.